Hello, everyone. We are starting chapter 15, but before we can start it, we need to have a little bit of background knowledge about some graphs. And so I thought we'd spend today's lesson just looking at these new types of graphs that you wouldn't have learnt yet in methods. And these are cubics and the sine and cos functions, which are related to the unit circle. So that's what we're going to be learning about today, these three graphs, and our main aim is to be able to sketch them and also to be able to find the key points in these graphs. So I just really wanted to start off with how do we know what a graph looks like in the first place? So if we think about a linear graph, so we're going to think about the function x plus 2. What we would do is we would start by finding different x values. So if this is x and y, this will be -3, -2, -1, 0, 1, 2, 3, and then all we simply need to do is substitute each of these x values in to find a corresponding y value. So for example, when x is -3, then y will be -3 plus 2, which will be -1. And then we can try with -2, y is equal to -2 plus 2, that's equal to 0. So we can see that we are going up, in this case by 1, and more importantly, the reason that we know that is because the gradient is 1. That's the number in front, so we're going to go up by 1. So I can very quickly and easily fill in these values. Now what we would do from there is go ahead onto a Cartesian plane and plot each of these points. So using an appropriate scale, my scale's a little bit off, but it's good enough. We can go ahead and put in these values. So -3 and -1, -2 and 0, -1 and 1. Oops, that's a little bit off. 0 and 2, and so on. And so what we should get once we're done is a nice straight line that goes through your points. Clearly my scale is a little bit off. So if we just try and move that a little bit, I know that's a little bit dodgy, but you get the idea that we will be having a straight line that will connect all of our dots in a perfect straight line. So that's how we figured out what a linear graph looks like. We have all of the points, we connect it, and we find out that it's a line. Similarly with our quadratic, we would do the exact same. So if I have y equals x squared minus 1, in this case, again, I will find different values of x and y, and I can substitute them in. So when x is -3, y will be -3 squared minus 1, so that'll be 9 minus 1, which is 8. Then I can have the same thing with -2. Now, there's no gradient this time, so it's not going to be as easy, but -2 squared is 4 minus 1 is 3. And then we can kind of start to do it in our head. So this, for the next one, for when x is -1, well, -1 squared is +1, 1 minus 1 is 0. If I have 0, 0 squared is 0, minus 1 will be -1, and then 1 squared will just be 1, minus 1 is going to be 0, 2 squared is 4, minus 1 is 3, and 3 squared is 9 minus 1 is 8. And so perhaps you can see at this point that we actually have a little bit of symmetry that is happening here, and this is going to be the point, which is my minimum point in this case. As you can see, everything around this point is symmetrical in that that's 0, 0, 3, 3, 8, 8. We also know, hopefully from quadratics, that this is just our normal x squared graph that has been brought down by 1. So what we would normally do is get all of these points again onto our Cartesian plane. We'll see how accurately I can draw it this time. So -3 and 8 will be up here, -2 and 3 would be around there, -1 and 0, 0 and -1, and we will have all of these points here. And hopefully you can see what we'll have is a little bit of a curve that will go through these points. Now clearly I've completely missed the mark here, that's fine, but again, you get the idea of what your quadratic should look like. When you're not connecting the dots, it should make a nice curve that looks like this. So this is what we call a parabola, and that is going to be our y equals x squared minus 1 graph in this case. So what we're going to now do is we're going to move on to the next power, which is cubed. So y equals x cubed. So we're just going to get the base shape for now. So we're going to do the exact same thing where we're going to plug in all of these x values to be able to understand what that's going to look like. So that's x and that's y. x equals -3. When x is -3, y is going to equal to -3 cubed, which is going to be -27. When x is -2, y will be -2 all cubed, which is -8. When x is equal to -1, I should start filling these in. Y will equal to -1 cubed, which is -1. When x is 0, then y will be equal to 0 cubed, which is 0. And then have a look at what starts to happen now when our values repeat, but they're just going to be the positive version. So now when x is equal to 1, y will be 1 cubed, which is 1. And you can hopefully get the idea from here. 2 cubed will be 8, positive, and 3 cubed will be 27. So it is so similar to the quadratic. As you can see, there's a point at which there is the axis of symmetry. That's what we would usually call it with quadratics, because the values are exactly the same. In this case, they look almost the same, except one side is positive and one side is negative. So how does that actually affect my graph? Well, if I go ahead and try and draw my graph in, I think if I put the -3 in, it's going to be too wide of a scale. So let's just go for -2, -1, and 0. And you can imagine that where 3 is going to sort of be off the charts in this case. But we have our key point here, which is 0, 0. I will try and get as accurate as I can a scale. So that will be 8, half of that is 4, half of that is 2, and half of that is 1. So that'll be 1, 1, and then 2, 8. So you can see that this side kind of looks like a parabola, but unlike our quadratics as we just had before, because I'm not squaring them, so my numbers were not going to become positive. In fact, when I cube them, negative numbers remain cubed. So it's going to look like the parabola, but my negative numbers can remain negative. So that's exactly what's going to happen. And you can imagine that if I had the 3, then it would just be a very steep number. So I would have this part and this part. Okay, so that is what my cubic looks like. It's probably meant to be a little bit more flat on this end. I'll just give it one more try and see if I can get it a little bit more flat. It's not quite working, but anyway, that's what it'll look like there. Now with our quadratic, we have this special point here. I'm going to do it on this one because it's not as dodgy, but we have this one called the turning point. Usually it's our H and K. In this case, we don't have a turning point because it doesn't turn, but what we call it is a point of inflection, because what it does is it inflects, as in it stops for a moment and then it continues. So it's kind of like it's shaped. It just inflects. It shifts in that kind of a shape. So that's what we call the point of inflection. Now, very similar to our quadratics, we also have a general cubic formula. So that's y equals x minus h cubed plus k. Of course, you can have an a in the front, except this time the h and k make that point of inflection. But everything is the same. H tells you how much it moves left and right, and k tells you how much it moves up and down. So if we were to do another example, but with a transformed cubic, so say I have y equals x minus 2 cubed plus 1, well, all I need to know is that the point of inflection is 2 and 1. Of course, the sign changes as it does with quadratics, and I can draw that in pretty much straight away. So here is where 2 and 1 would be, and then we go upwards and we go downwards. Now, of course, the only thing is, I mean, it could have gone this way, or depending on the intercepts, it can go that way. So you really should check before you go ahead and draw it. To find the intercept, it's very easy. It's very similar to everything you've done before. So to find the y-intercept, we make x equals 0. So that'll be 0 minus 2 cubed plus 1. Negative 2 cubed is going to be -8 plus 1 will be -7. So in fact, I just happened to draw it correctly, but I probably wouldn't take the chance in the future. But the y-intercept is at -7. For the x-intercept, we make y equal to 0. So that'll be 0 equals x minus 2 cubed plus 1. I'm going to take the 1 over, it becomes -1. I'm then going to take the cubed root of both sides. So the cubed root of -1 is just -1. So that'll be x minus 2. And then I take 2 over. So that'll be plus 2. -1 plus 2 is going to be +1. So that's my x-intercept there. Obviously, my scale's a little bit off. So that's just an example of how you sketch a cubic. That's all the cubics that you need to know at the moment. You don't need to know it in expanded form, but as long as it's in this particular form with your H and K, which is your point of inflection form, then you will be able to sketch the cubic. The next two graphs that we're going to look at are the sine and the cos function. So we need these both for the coming exercises. And I just wanted to very quickly review our idea of the unit circle that we looked at when we looked at complex numbers. So the unit circle is, it looks like this. So the unit circle has a radius of 1. So this point here would be 1 and 0, 0, 1, -1, 0, and 0, -1. And if you remember, if this unit circle, so one unit, has a radius of 1, the physical distance to get to this point, the physical distance of half of the circumference is 3.14 centimeters, which is what we call pi. So that's where we get pi. This is only half of that way, so that'll be pi on 2. Of course, if we were to go the whole way around, so that's 1 pi, that will become 2 pi over here. So that's the same value at 0 and 2 pi. And of course, this here is 3 on 2, so 1.5. So that'll be 3 pi on 2. Now, what we also learnt was about the measuring system called the radian. So the radian was in regards or in terms of pi. 1 radian was where the circumference of the circle or that segment matched the radius. So pretty much when I had 1 here, because the radius is 1, then that makes 1 radian. That's why this is 3.14 radians, because that's the physical distance of it. In terms of our ratios, what we then looked at was, well, what if I have a triangle that looks like this? So if I have this point here, A and B, and I wanted to know the actual value of that, well, first of all, this is the radius, so this is going to be 1, as we know about. I'll just move that over here. So the x distance, so from here to here, as we know, that point is A, because that's the horizontal value, and from here to here, that is B, so that's the vertical distance. So how can we actually find that distance out? Well, if I know what this particular angle is, so if I know what that particular angle is, let's say I want to try and find this A. So A is adjacent to this, and what I also know is the hypotenuse. So if you think back to your SOHCAHTOA, so SOHCAHTOA, what uses both adjacent and hypotenuse? That's cos. So I can actually find cos theta is equal to A on 1. If I multiply the 1 over, or in this case, I mean A divided by 1, I find out that cos theta is equal to A. Now, more specifically, what does that mean? Our A is our x value. So in general, cos theta will always be our x value. So you can always think of whatever your x value is, that is what cos theta equals to. Now, in the same way for B, B is our opposite side. So what uses opposite and hypotenuse? That's sine. So sine theta is equal to opposite over hypotenuse. That will simplify down to sine theta is equal to B. Of course, what is B? B is my y value. So in general, we can say that sine theta is equal to our y value. Now, how does that help me? Well, what that means is that any point around the unit circle, instead of saying it's x and y, is cos theta and sine theta. So for example, this point here, look, 1 is equal to cos theta and 0 is equal to sine theta. What does that mean in terms of my unit circle? Well, I can now find different angles. So for example, if I draw up over here, if I want to find out what is the sine value at pi on 2. So what this is trying to tell me is what is the y value at the point of pi on 2. That's over here. What is that y value? Well, it's just 1. So now I'm able to find out what that value is there. Similarly, if I wanted to do cos of pi, well, that's just saying to me, what is my x value at the angle pi, which in this case would be -1. So it's very important because in a sec, we're going to try and find what are our x and our y values to be able to sketch. So you just have to remember your cos value is x and your sine value is y. So now what we're going to do is we are going to start looking at our graphs, and the first graph we're going to look at is y equals to sine x. So that's the function. I know that we just said that y is equal to sine theta. I want you to think of y as the function, what it equals to. So it's different to the fact that sine theta is equal to y. I'm now looking at, it's just like y equals x squared, but now it's y equals sine x. So how can we find out what sine x actually looks like? What we can do is we can substitute in all of these different values in order to be able to find that. Now it looks like quite a lot. I'll be able to try and summarize it quite quickly. So we'll start off with this point here, sine of 0. So what we're trying to say is, what is the y value when x is 0? Or when, sorry, not when x, in this case x is the angle, but what is the y value when the angle is 0? In this case it's x. If we have a look back here, here is my angle of 0. What is the y value at this point? Well, it is also 0. So that's for that point there. Now the next one is sine of pi on 4. I'll come back to that, but that needs your exact value table, which we used last time with the complex numbers. Let's go to pi on 2. So what is sine of pi on 2? So again, what that's saying is, what is the y value when my angle is pi on 2? In this case, it's 1. So if you'd like, pause the video here for a second, see if you can fill out the rest, and I'll continue on. So if we look at pi, what I'm saying is, what is the y value when when the angle is pi? In this case, it's 0. When it's 3 pi on 2, the y value will be -1. When it's 2 pi, it's 0. 5 pi on 2. So when I go all the way around at 2 pi, 5 pi on 2 is just another pi on 2. So we're back here, back where we started. So that will be 1. At 3 pi, it'll be 0, -1, and 0. Hopefully you're able to see the pattern here. So even when I go backwards, again, we'll leave negative pi on 4 for a second. Negative pi on 2 means I'm going backwards. So backwards by pi on 2, which is a quarter of the circle. That means that's -1 there. And then that will be 0. Now what happens at pi on 4, I'm not sure if you remember your exact values table, but you can pull that out. And there's a specific value that we have assigned to that, which is 1 on root 2. So it's not a half, which is what we would expect, it's 1 on root 2. And then, of course, this would be -1 on root 2 because sine is negative. Now, what we're going to do, we're not going to graph it for this many values, but I will graph it between 0 and 2 pi. So I'm just going to put in all of my key points. I'll ignore the pi on 4 for a sec. So these are all of the key points because these are the key angles. So 0, pi on 2 pi, 3 pi on 2. You must remember these because they're your key values. So that's pi on 2, pi, 3 pi on 2, and 2 pi. Of course, we do have our little pi on 4 that's going to help us graph as well. Now I'm going to put in all of these key points at first. So 0, and of course I will put in my y values as well. 1, 0, -1, and 2 pi. So it kind of looks like it would be a zigzag. So we need a little bit more information, which is why we have this pi on 4. So that value there is in fact going to be a little bit greater than a half. So when we start to put in these values, what you'll notice that in fact it's not a straight line, but it is a curve that looks like this. And because the unit circle just repeats over and over, so does our graph. So our graph is just going to continue on forever and ever doing this. So that's how I can graph the negative side as well. So it'll just look like this, and I can fill in my values as appropriate. So that would be -pi on 2, and that would be -pi, and so on. So that there is my sine graph, y equals sine x. So you can figure out what it is by substituting in different x values, which in this case are the angle, to be able to find the corresponding y values. So what you'll notice is that there's a few properties that we need to note. So the first thing is that the graph repeats itself after an interval of 2 pi units. So what that means is after we hit 2 pi, it starts repeating. And that makes sense because the circle is 2 pi. So when I hit that point, I just start repeating my values over and over. What we call this is the period of the function. That's called the period of the function. So the period of a sine graph is 2 pi because it's going to repeat every 2 pi. The maximum and minimum values are 1 and -1. The reason for that is that the unit circle, the maximum value is 1 and -1. But you could imagine if I'm using a circle that's got a radius of 2, well then the radius at the maximum and minimum will become 2 and -2. And finally, the distance between the mean position and the maximum position is called the amplitude. So what that means, the mean position is the middle and between the maximum. So if my graph looks like this, what we're saying is that this distance here is called the amplitude. The amplitude is a distance, so it'll never be negative. So even down here, when we're looking at -1, that will never be negative. So this is a summary of what the sine graph looks like. Now, if you go ahead and do this exact same exercise, then you will notice that the cos graph looks like this. So just a couple of key points, for example, if we have y equals cos x, this time when x is 0, we are trying to find out, well, what is the x value when the angle is 0? If I go back to the unit circle, here is the value when the angle is 0, here's the x value, which is 1. So you'll notice that it's the opposite, which is why it looks a little bit different. So that'll be y is equal to 1. And that's why all of the values are the way they are. X is 0 at pi on 2, it's -1 at pi, it's 0 at 3 pi on 2, and then it's at 1 at 2 pi. But what you'll notice is, again, what's going to happen after this point is it starts to repeat. So again, it has a period of 2 pi and the amplitude of 1. So that's our maximum value from the middle point. So just like with every graph, we do have transformations that occur. So we have our h value and k value, which moves it left, right, up, down. You don't need to know much about the left, right, but I will briefly talk about the up and down. The A in the front is going to be my dilation from the x-axis. So what that means, from the x, if I start at the x, I'm moving away from it. That means it affects the y values. This, in fact, is the amplitude. It tells me how wide it's going to be. And this value inside n is another dilation. I know it looks a little bit funny. You'll learn about this a little bit more next year. But whatever value it is here, it's 1 on n, 1 on that value away from the y-axis. What we mean by that is here's the y-axis. That's going to change there. So in general, that's going to help me find my period. And the period is always 2 pi divided by this value, because the period is normally 2 pi. And then we divide it by this n value to give us what our period is going to be. So let's go ahead and practice this with a few examples here. So for part A, it says for each of the following, state the amplitude and period, and I'm also going to get you to sketch it. So in this case, the amplitude is the value in the front, and the period is 2 pi on n. In this case, n would be a number in front of x, which is just 1. So in this case, it's 2 pi divided by 1, which is just 2 pi. Now that I have this, I can go ahead and sketch. So all of my key points is always pi on 2, pi, 3 pi on 2, I didn't draw this big enough, and 2 pi. Just move this arrow out of the way. And then my maximum is 3 and my minimum is -3. So now I can go ahead and sketch my sine graph, which looks like that. For part B, the amplitude is the number in the front. In this case, it's 0.5. And the period, as we said, is 2 pi on n. In this case, n is 4. So that'll be 2 pi on 4, which is pi on 2. Now, how does that affect my values? I'll show you as we graph it. This time, that means one cycle is going to go for pi on 2 rather than 2 pi. Now, also, this is a cos graph. So I'm just going to do this one a little bit differently, where I'm going to actually sketch it before I put in my values. So we know that our period, as in my cycle, is going to last pi on 2. Here, 2 pi is the end. You'll notice that its midpoint is just middle of that, and then this point is half of that as well. So we're going to do the exact same thing. My midpoint is going to be half of pi on 2, and then this point is half of that, which is pi on 8. Now, how do I find this value? Well, that is this value 3 times. So in this case, pi on 2 times 3. And same thing here, pi on 8, but then times 3. So that will be 3 pi on 8. and that is how you do your graph. Of course, we just want to include the amplitude, so that will be 0.5 and negative 0.5. The last example that we're going to do will be this graph here. I'm just going to change just one thing in it just to help us with a bit of transformations. This time what I'm going to do is I'm going to add a +1 at the end. So the whole graph I actually want to lift up by 1 in the end. As always, amplitude in this case is a half and the period is 2 pi on n. In this case, the n is a half. So that's 2 pi divided by a half, which will be 4 pi. So with all of our key points, as we talked about before, we're going to be dividing it to be able to find the other points, dividing it by half and then half again. Now, this time what's happening though is that the whole graph is being lifted by 1. So how does that affect it? Well, this is my little trick to be able to do it with a different color, maybe with a grey lead so you can easily rub it out. I will draw another line at 1 and that becomes like my new fake axis. So from there, I'm going to draw my cos graph. So if this point, the middle is 1 and the amplitude is half, that means that's going to go all the way to 1.5 or 3 on 2. And if my starting point is 1 and it's going to go a half underneath that, well then that is going to go to only 1/2. So I think I do need to change this so the scale matches a little bit more. So my lowest point will be at 1/2. Just change it a little bit more. There we go. And now what I'm going to do is I'm going to draw this graph pretending like this is the x-axis. So I'm just pretending that that is the x-axis. So what would that look like? Well, my cos graph would end up looking like this. So it's as if this is the x-axis, but it's not. What are my key points? Well, this last point, it's on the x-axis, that's 4 pi, as we know that's our period. And then again, we'll do half point. So this halfway point there is 2 pi. This point here will be at half of that. And then this point is 3 times the initial. So that's 3 pi. So this is how you graph it. Now, in case this graph, instead of going upwards, goes downwards, you would usually find your x-intercepts, but at this point, you don't need to worry about that. And that's it. That's all you need to know for our graphs going forward. So what I'll do now, you've got a couple of exercises that will be on sector just to try and help you with these graphing techniques. I know it's a lot in one lesson. You don't have to stress too much about knowing the ins and outs of these, but I do want you to be familiar with these graphs to be able to help you with next lesson. Best of luck and have a lovely weekend.